Bismillah ar-Rahman ar-Rahim. Today we are going to start the second part of Verilog. The previous part was about structural models, like the gate netlist models, okay, as well as very minor information about behavioral modeling using continuous assignment statements, okay. Now this chapter or this unit is going to focus on behavioral modeling, okay? So we are going to talk about behavioral modeling, including always block, procedural statements, if statements, procedural assignment statements, of course, if statements, case statements, and then we'll give some design examples, okay? So first of all, what do we mean by behavioral modeling? It means that I'm going to tell the system, or I'm going to tell the compiler or the synthesizer what the design will do, okay? I'm not going to tell it how it will do it, okay? How my system does what it does, but I'm going to tell it what it will do. For example, my system adds 2 binary numbers. That's it. I'm not going to tell you how to do it. You, as the compiler, as the synthesizer tool, you should be able to figure out how to do that yourself, how to build the system yourself, and help me doing that, okay? I don't have the time to do it myself, synthesize my system. So I'm going to give you, I have so many tasks to do. So I'm going to give you all my synthesizer. I'm going to give you behavioral description of my model, and then I want you to convert that to a structural model. This is synthesis, okay? This is the synthesis tool. So you take synthesizer, basically a synthesizer. Let's just draw this. A synthesizer, what does it do? Synthesizer tool. It takes, for example, behavioral model, and then produces for example, structural model or circuit or netlist. Okay, so this is the synthesizer. So you tell it, for example, you tell it that my circuit adds A plus B, 2 binary numbers, and produces the carry out and the sum. Okay, then you give it in terms of behavioral model, Verilog behavioral model, and you feed it to the synthesizer, Xilinx, for example, synthesizer, and then the synthesizer will produce a netlist for you that is that maps one-to-one to hardware, okay? Hardware synthesis of your behavioral model. So the behavioral model, okay, tells the system or the compiler what my circuit does, but it doesn't tell it how it does it, okay? And this helps you in rapid behavioral prototyping of a design, okay? And it helps you also to verify the functionality. It also, by using the synthesis tool, okay, you don't need to actually do the structural model yourself. Okay, so the synthesis tool will take care of that for you. Okay. Also, behavioral models can be thought of as a documentation of your system. In order to see how this black box works, okay, you just need to examine the behavioral model. You don't need to examine the structural model, okay? And it will be very easy to see what the model does when you check the behavioral model. Yes, question.
Like in Python, you mean libraries, you go to documentation and get the information.
Some sort of, yeah. I mean, what I mean is
Yeah.
that the behavioral modeling itself is very easy to understand, and it can be considered as a documentation by itself, not including comments, of course. By itself, it can be considered for experts like us. Okay, it can be considered as a documentation. Okay, without underestimating the power of normal comments and documentation. Okay, all right. But you're right. Documentation. I mean, by documentation, I mean it is a document that you refer to understand the functionality of uh, uh, a given, for example, system or library. Okay. So, what about the data types for behavioral modeling? I mean, this is nothing new. There is nothing new here for us. We already know about wires and registers, but the only thing that is new here is the introduction of bit vectors. Okay, bit vectors means if you have, for example, a wire X, for example, named X, then the size of this wire is implicitly implied to be one. It's one bit, just one wire, one bit. Okay, so this is X. So this is going to be one. Okay. If it is one, then we don't write it. Okay. And hence we don't give the size here. Okay. However, if you have like, for example, Y that has, let's say, three wires. Okay. This is Y 0, and this is Y1, and this is Y2. Then how do you declare that? Using wires. You say, well, wire, and then you give it the size here, 2 to 0, and then you say Y. So this tells us that Y is how many bits? 3 bits, 2, 1, and 0. Okay, where 2 is the most significant bit and 0 is the least significant bit. Okay, so this is how you declare a bit vector. Okay, bit vector. So, similarly, for registers, it's the same idea. Okay, but you replace wire with register. Okay, all right. Don't worry about these. Okay, integer and real and time and stuff. These are important, but for us at this level, they are not really that big deal. Okay. Yeah, when you would like to specify a constant in Verilog, you can specify it using any base. I mean, any of the four most famous bases: decimal, octal, hexadecimal, and binary. Okay. Well, let me give you an example. So, if you would like to say, well, I would like to represent the number 5 in binary. Okay, 5 requires how many bits? 5 requires 3 bits, right? So you write 3, which is the size first, and then put a single quote character. Okay, single quote character, and then you say the base B. Okay, and then you write the 5 in binary 101. If you'd like to write it in decimal, then it's going to be, again, it's 3-bit, same number, 3-bit. Okay, B, and then not B, it's going to be D. Okay, and then you say 5. Hexadecimal, again, you replace D with H. Octal, you replace D with O. Okay, so the size is always in the number of bits, and the size can be ignored completely. The size can be ignored completely. So if you say, for example, D 27, for example, then this number here is inferred by the compiler to be how many bits? Who can tell me how many bits is this? It's going to be 5 bits, right? 5 bits. So this number here is going to be inferred to be 5 bits. Okay. All right. Now there is an issue when you have when you specify a number that doesn't fit in the size. in the specified size. So for instance, you have, for example, 3, okay, as a size, and then you say, well, the 17, for example. Yeah? Now 17 requires how many bits?
4.
It's 5, actually. 5 bit. Yeah, because 15 is the maximum number for 4 bits, and then 16 and 17, both 5 bits, okay? So the representation for this is nothing but 10001, right? So what the compiler will do is that it will truncate the most significant 2-bit and get the least significant 3-bit. Okay, so your number, this is going to be by the compiler's eye, this is going to be equal to 1. Okay, let's take another example. For example, 5. Okay, and then let's say, for example, H A no, let's say, for example, 9C. Okay, so this number is going to be converted by the compiler's by the compiler. It's going to be truncated to what? First of all, this is an 8-bit number, but you're specifying the size to be what? 5-bit. So the most significant 3-bit will be truncated, right?
Yes.
So in binary, this is going to be 1 and then 1100. So this is going to be 1C, yeah? 1C, right? Which is 16 plus 12, which is 28, yeah, in decimal. All right. So this is excellent questions, by the way. There are lots of tricks in here, so just pay attention to this. Okay. Now we talk about Verilog operators really quickly. Okay, and we have seen this concatenation operator before. We've used it in the designs. Okay, but we are going to now visit it formally. Okay. So we have here a number of operators. One is the concatenation and arithmetic, and then relational operators, and then logical. Okay, don't worry about the case. All right, case equality. The conditional. Okay, this is the one that you use in C and Java. Okay, bitwise operators and reduction operators. Okay, and then the shift left. We'll talk about each one of them in the next few slides. Okay, so for arithmetic operators, if you use a plus or a minus, and this will infer the use when the synthesizer does its job by converting your behavioral model to netlist, it will infer the usage of an adder subtractor. Okay, so plus or minus, you will infer the usage of an adder or subtractor. Okay, the multiplication, not all the synthesis tool provide you with multiplication functionality, but Xilinx does that. Okay, and so it can infer a block multiplier during synthesis for multiplication operator. However, there is no tool, okay, or only very few tools that can provide the division operator, okay, and none of the tools provide you with the synthesis for modulo and exponentiation operator. So you have to do that yourself, unfortunately, if you need them, but most likely that you don't. Okay. The shift operators, okay. Basically, we have arithmetic and logic shift. So this is logic shift and this is arithmetic shift. And the best way to represent them is to introduce them is using examples. Okay. Now for shift, it is nothing but changing of wires. Okay. you change the wires. There is no hardware required, in fact. Okay, so the synthesis of the shift is very easy. Okay, um, so let's suppose that my A, okay, contains this number here. Okay, my A is 8-bit and it contains this number. All right. So what is A shifted to the right by 2-bit? This is what it means. A shifted to the right by 2-bit. It means that I'm going to get rid of the least significant 2-bit and put zeros here, since this is a logical shift. Okay. So my answer will be 0, 0, 0, 1, 0, 0, 1, 1. Okay, as given here. Okay. Again, I don't want to introduce the arithmetic shift here. Okay, and I advise you to use the concatenation operator to implement arithmetic shift. Okay, do not use the arithmetic shift operators in Verilog. Okay. Now for shift left, logical shift left. Okay, what do? We have A here. Okay, so we are shifting this way, right? So shifting this way, we have zeros here. So we have 2 zeros here, and then we get rid of the most significant 2-bits. So the answer will be 0, 0, 1, 1, 1, 1, 0, 0. Exactly like this. Okay. You're given another example just to do it yourself. Okay. Any question here? Now for Verilog operators, okay, for relational operators and equality operators, these are the greater than and the sisters, okay, and also equal and not equal. The usage of these operators in your code, in your Verilog code, implies comparators in the synthesizer. Okay, the use of comparators in the synthesizer. Okay, what about bitwise operators? Bitwise operators means that you are performing the operation bit by bit. Okay, for example, if you have, this is the definition of A and B and C. Here they are wires of size 4. Okay, A, B, C. And the usage of this bitwise statement here, C, which is 4-bit, is equal to A, which is 4-bit, ORed with, bitwise ORed with B. Okay, so this translates to, this one here translates to these 4 statements. Okay, so C3 is equal to A3 ORed with B3. Okay, and then C2 is A2 ORed with B2, and so on and so forth. You see that? So this statement here saved you 3 more statements. It's just so powerful. I mean, bitwise operations are really helpful, and without them, you will have a lot of trouble trying to do just this simple operation here. Okay. All right. What about reduction operators? What does it mean? It means that you take, for example, reduction or reduction of A. It means that you are ORing all the bits of A and assigning it to something else. So for example here, if you assign Y to be the reduction of A, the reduction OR of A, and A is 4-bit here, then Y, this is essentially the same as assigning Y to be A3 ORed with A2, ORed with A1, ORed with A0. Okay, so this is just a shortcut for doing this. Imagine that A is 64-bit. Okay, and imagine the amount of time that this statement here saves you. Okay, so these are reduction operators. You can use OR and an XOR as well. All of them can be used for reduction operators. Okay. What about logical operators? Logical operators, okay, you can see that the difference between logical and bitwise. Here, bitwise is single ampersand, operator, okay, and single pipe and single XOR and exclamation point for not, okay. For the logical operators, it's double ampersand and double OR and exclamation point for the logical negation. We don't have an XOR here. You can implement it using the and and or, okay, and not, of course, okay. So what's so special about logical operation? It's a logical operation returns either true or false. It doesn't return multi-bit like the bitwise operation, okay. So if you have, for example, a that is let's say that a is 5-bit and it or 4-bit and its value is 5, and b is 3-bit or even 4-bit and its value is 7, okay. What is let's pick another example here, 9 for example, okay. What is a ORed with b? Who can tell me? So it's 0 1 0 1 ORed with 1 0 0 1, right? And the answer to that is what?
1 1 0 1.
1 1 0 1. Excellent. Yeah, this is the bitwise OR. What about a logical OR with b? It's going to be a 1. Why? Because it's non-zero, ORed with non-zero. True, ORed with true is true. Okay? So do not confuse the logical operation with the bitwise operation. Bitwise operation produces a number, an integer, whereas the logical operation produces a bit, which is true or false. If your bitwise operation produces a bit as well, then you can use it as a logical operation. Okay? There is no difference now. Okay? What about any question here before I move on? Okay. What about
دكتور كيف طلع واحد؟
Yeah, because this is when you say here, you can think of A and B as a result of comparators, okay? For example, A is X greater than Y and B is X less than Y, okay? So non-zero, usually non-zero in logical realm, okay, is true. And 0 is false, okay? So here we have non-zero, ORed with non-zero. What does it mean? Logical ORed. So it's true ORed with true, which is true, which is 1.
Okay.
You see that?
Yes.
What about A logical ANDed with B? What is this?
True.
True. Also true.
1. Yeah.
Yes.
What about I think there is I think this should be this, not, let me see. Yeah, there is a mistake here in the slide. Okay, there's a mistake. Yeah, see, logical not, and this is bitwise not. Okay, so here bitwise operation, this one here, let me see, this one here is not correct. This is not correct. It should be the tilde character. Okay, it should be this character. All right, this is the bitwise not. Okay, so I was trying to tell you here, okay, to give you an example of not A ORed with not B. Answer is
0.
0. Excellent. Yes. Okay. So not A is going to give you a 0. Okay. Because A is non-zero, so it gives you a 0. And not B is going to be a 0 as well. So 0 or the 0 is 0. Okay. Okay. What about this operation here? You have seen it in Java and C. For example, you can say, well, assign max to B. If A is greater than B, then it's A, otherwise it's B. So this translates to an if statement, like, for example, if A is greater than B, then max is equal to A, else max is equal to B. Okay, so this is what it means. Have you seen it before?
Yes, yes.
I've seen it in the lab. We use it with the multiplexer.
Yeah. So this is exactly, we can use it as a multiplexer, of course. So for the multiplexer, you have, for example, the selection S. If S is 1, then you use you output what? You output D0, D1, else it's D0. See that? You can use it. Okay? We'll see in front in the upcoming slides. We'll see examples of behavioral implementation of multiplexers. What about concatenation operator? Okay, concatenation operator. Okay, is we have seen it before. Okay, but here we are showing how to implement rotation, shift, arithmetic shift, and logical shift using this operator. And we have seen how to do that before, but this now introduce the idea formally. Okay, so here we have an A here, which is 8-bit. Let me try to do that here. Okay. So we have an A, which is 8-bit. Right. So this is bit number 0, 1, 2, 3, 4, 5, and 6, and 7. Okay. And I'm going to copy this 2 times because you're going to use it 2 times. And so here. Okay. So what we are going to do is we have A, which is basically 8-bit, and we are going to rotate A by 3 to the right, okay, and store that in the variable ROT. Okay, ROT is going to be rotation to the right of A by 3-bit. Okay, what does rotation to the right mean? It means I'm going to take this bit here and rotate it back to the most significant bit. And then the most significant bit will go here, and then this will go here, and this will go here. Do you see that? We'll do that 3 times. Okay, we'll do that 3 times. So this will go here now at the beginning. This will be here. Okay, and then everything else will be shifted here. Okay, so the 1 will be here, and the 2 will be here, and etc. Okay, you see that? But we are going to do it 3 times. So we are going to take this completely and put it in the front here. So what this means is that, okay, this part here is going to be moved here. So basically my my ROT is going to be A, which is A what? A2 to 0, right? Concatenated with A what? 7 to 3. See that? So this is my rotation is going to be assigned, right? And I use concatenation operator to concatenate these 2-bit strings here. Okay, A 2 to 0, comma, A 7 to 3. Do you see that? Any question here? The next one is a shift left shift to the right. I'm sorry, shift to the right by 3 bits. Okay, and logical shift. It's logical shift. So we insert zeros instead of the sign bit. Okay, so we shift right again. We shift right so that the direction of the shift is this way now. Is this way. All right, and here we insert zeros. How many zeros? 3 zeros basically, because we are shifting 3 by 3 bits. Okay, so here we have our new bits. Okay, so we must get rid of the least significant 4 bits. So this is basically nothing but a 3-bit, okay, of you can say binary 0. Okay, so a binary number that is 0, and it's of size 3. This is important to it is very important to specify the size here. Otherwise, you will not. You will have either 0-bit, 1-bit, or it will be actually be more than that. Okay, it will probably be interpreted as an integer, which is 32-bit. Okay, if you don't specify the size. Okay, well, and what about this? Now this portion here is what? Is A 7 to 3 again. Okay, we have done this. So my variable is called what? It's called shift left. Yeah, shift left is equal to 3-bit binary 0. Okay, comma what? A. I hope that you guys are following. A what? 7 to 3. Okay, you see the power of concatenation operator now. Okay, what about shifting to arithmetic shift to the right by 3-bit? Okay, so again the shift direction is this way, but I'm shifting now. Instead of shifting in zeros, because this is arithmetic shift now, I'm shifting in the sign bit. What is the sign bit? It's bit number 7. So how many times do I shift it? 3 times. Okay, this is as specified by the example. Okay, 3 times. So I have my 3 new bits, and I get rid of the old 3 bits. Okay, so again, this is going to be assigned shift right, arithmetic. What's it called? A? Yeah, A. So it's going to be what? Who can tell me?
A7 3 times.
A7, excellent. Yeah, 3 times. I mean, there is also a replication operator you can use, but we haven't discussed it. We don't discuss it here, but it's okay. You can just like that without being lazy. Okay, A7, and then what?
A7.
A7
7 3.
The 3. Excellent. What if? Okay, just a final example. I want to shift to the or rotate. Let's say rotate to the left. Rotate to the left by 2-bit. What is the answer? So assign rotate left 2. Okay. So just imagine that. So I'm rotating to the left now. So the rotation is this way. Okay, and it's just it's coming back to here. Okay. You see that?
Yes. A520.
Excellent. Yeah, A5 to 0, and then followed by
A76. لا, yeah, yes, 76.
7 to 6. Excellent. Yeah. Okay. You get it, guys? Okay. So this is about the concatenation operator. So this is our first example of a behavioral description of an adder. Okay. So look at the beauty of the description here. We don't provide any details here, any AND gates or full adders or something like that. We just give it the behavior of the adder. Okay. So we say, first of all, we have a parameter here. We are defining a parameter. So the parameter name is width. Okay, this is how you define give a parameter to your module. Okay, pound, and then you have brackets, round brackets, and then you have the keyword parameter, and then the parameter name, and then the default value of the parameter. The default value is handy because if you don't provide the parameter during instantiation of the module, it's going to be the default value. Okay. Now the output C out is just a single bit. You don't have any. The carry out is always a single bit. Then you have the sum, which is supposed to be width -1 to 0, right? Width -1 to 0. All right. Because I have 4-bit now. If I have 4-bit, then this should be 3 to 0. Okay, and then A and B, which are width -1 to 0, and then B with Cn, which is just 1-bit. So now I'm using concatenation operator, okay, here to concatenate C out with sum, and then assign this to A plus B plus Cn. So the least significant or the most significant bit will go to C out, and the least significant width -2 bit will go to sum, or width -1. I'm sorry, width -1. No, actually, yes, it's the width bit. I'm sorry, the least significant width bit will go to sum. Okay, so if width is 4, the least significant 4 bit will go to sum, and the most significant bit will go to C out. Okay. So C out, comma sum here. This is sum. This is supposed to be sum, not S. Why is that? Sum. And it's also remember that Verilog is case sensitive. So S is small here. Is a 5-bit bus. We call it a bus. Okay. So it has like wires here. C out, S3, S2. S1, S0. Of course, these are supposed to be called sum 0, sum 1, sum 2, but it's okay. You get the idea anyway. Okay. So we have a module and in module. So we are implementing this using a sign statement here. Okay. Sign statement. Remember, it's a behavioral method to describe your circuit. We're not actually giving here the actual implementation, but rather we are giving the functionality here. Okay. So this is extremely simple. It's just 2 lines of code or 3 lines of code. Module, and then the assign statement, and then end module. That's it. Next example here, or next we are going to discuss the always block, which is an extremely powerful block that will allow even more sophisticated functionality. Okay. So basically the always block, it contains what we call sequential statements. Okay. sequential statements. And this is how you define it. Always, and then at, this is just at is the syntax, part of the syntax. It doesn't change. And then between round brackets, you have your sensitivity list, and then begin and end. Okay. So the sensitivity list is going to tell the compiler or the synthesizer when is this block going to be executed. So if you have A and B, for example, here, then any change in A or any change in B will trigger execution of this always block. Okay. Let's see examples. So, but before I see examples, there are two types of sensitivity list variables. One is called the level type, in which you give it the variable name only, and the other is called the edge type, which is at the positive edge of the clock, at the negative edge of the clock. We will talk about this positive edge and negative edge in the next module of Verilog, okay, or on the next Verilog presentation. Right now, well, all we have to worry about is the level edge trigger. So this means that any change in A, B, or C, execute this always block. Okay, let's take let's talk about what we call procedural assignment, which is different from continuous assignment. Okay, there are two types of procedural assignment. One is called blocking, okay, and the other is called non-blocking. This is how you do the blocking assignment. Okay, you use equal sign, and non-blocking you use less than or equal sign. Okay, so this is like a backward arrow, like this. It's an arrow to indicate the assignment here. Okay, so the non-blocking assignment is usually used for sequential circuits. So we're not going to use it this time. This time we are going to use blocking assignments. Okay, so blocking means the next statement is not going to execute until this assignment is executed. Okay, so it's used for combinational circuits. Okay, non-blocking, on the other hand, it doesn't block the execution. Okay, all non-blocking assignment in the same always block are going to be executed in parallel. Okay. Okay, I think the best way to discuss this is by examples. Okay, so we have here the if statement. Okay, so notice that if and case statements can only be inside an always block. Okay, you cannot have an if statement outside an always block, or you cannot have a case statement outside an always block. Here we are defining an ALU using behavioral modeling, okay? An ALU, a complete arithmetic and logic unit, using an if statement. The width of your inputs is called n here, and is passed as a parameter with the default value of 8, okay? And we have an output that is a register now, okay? The output, if the output is sit inside the always block, it must be of type register. Okay, it must be of type register. This is important to remember. If I repeat, if the output, okay, if the output is sit or is assigned inside an always block, it must be declared as a register, not as a wire. Okay. If you assign C in here outside using an assign statement, for example, you don't have to declare it as a register. Okay, it can be declared as a wire. Okay, in fact, it has to be declared as a wire. Okay. So we have an output reg, okay, which is C, okay, which is also in bit, and a selection functionality selection input, which is 2-bit S, and then A and B, which are in bit. So this ALU have 4 functionality. This ALU has 4 functionalities, and I have always this always block to be executed on any change of S or A or B. That's normal, okay? If any change in these inputs, then I execute this always block, which produces a new output for C. Okay, so if S now is equal to 0, 0 in binary, then my C is going to be A plus B. All right? Else, if S is 1, then my C is A minus B. Else, if F is 2, then my C is A and B. Okay, bitwise and. Else, finally, this is the final else, C is equal to A or B. And end for the always block, and then end module. You see that? Any question? So what is to conclude this lecture? I'm going to sketch the function table of this ALU. So we have S, which is 0, 0, 0, 1, and 1, 0, and then 1, 1. What is the functionality here? And for each one of the selection, for each one of the input. Yeah. So the functionality when S is 0, 0 is what? You can tell me according to the code here. Not F, this is C, okay? What is C here for 0, 0?
A plus B.
A plus B. And then?
A minus B.
And then?
A ANDed with B.
And then?
A
or B, yeah? So if I give you this, okay, suppose that you can do it using MSI components, right? We have seen even more sophisticated design than this, okay? So just make sure that you can synthesize this yourself, okay? So this is how the function table here is given, and this is how you do it using Verilog, okay? Using if statement. Next time we'll do the same using case statement, okay? Case statement is easy, okay? Let me stop here and pick up from here next time, okay?